So, on behalf of the Department of Metallurgical Engineering and Material Science, I welcome you all to this intriguing panel discussion on future of Indian steel industry in context of greening of steel. So with the world transitioning fast to net zero emissions, steel as a sector is in appalling need of transformative technological innovations, since only incremental solutions will no longer mitigate the environmental impact. To give some backgrounds to our newly joined colleagues, steel contributes to about 2.5% of India's entire GDP and 20% to India's manufacturing GDP alone. Interestingly, 50% of India's production capacity is shared by the top 10 players, whereas the other 50% is fragmented among various small players. We know India is the second largest producer of steel, yet its per capita consumption stands only at 74.7 kg compared to the world average of 225 kgs. This indicates that Indian steel requirements are meant to grow by leaps and bounds, and with it, the opportunities. But the major problem here is the CO2 emissions by the steel sector. It alone accounts to 8% of entire global CO2 emissions. Sadly, as evident in the infograph, only about largely 36.5% of the companies are doing nothing. Other 50% are only still in the acknowledgement phase. Yet 12.2% have started some long R&D projects, and only 3.1% have made any commitments to our net zero goal. And alarmingly, we have only 12.5% of these companies some pilot projects run to achieve our net zero goals. In the next slide, we can see the countries are arranged as per their CO2 emissions via their steel making route. And in the second infograph, we have countries' R&D expenditure. And here we see a direct correlation between the R&D spend of a country to its CO2 emission by steel making in that country. I think this indicates that it is time to give attention to the transformative changes in steel manufacturing that is required to reach our net zero goals. Through this panel discussion, we aim to understand the way forward in innovations for greening of steel and gain some actionable insights while we do so. Without further ado, I would like to invite and welcome our esteemed guest of panelists. First, we have with us Mr. Gajraj Singh Rathore, sir. He is the Chief Operating Officer of JSW Steel. Gajraj Rathore, sir, has been associated with JSW for now over 3 decades. Initially, he was posted at Vasant Works. He was also assigned at Tarapur Works, where in his tenure, he was responsible for the entire operations of the plant as the plant head. He has achieved various feats, looking after hot rolling, long products, steel melt shop, and iron zone. From 2017 onwards, he was promoted as the president and has been heading the manufacturing units at Dolvi and Salva near Mumbai. He is also in charge of the expansion of steel making capacity and making it double to 10 MTPA at the Dolvi unit. In 2022, he was given in charge of newly acquired plate mill at Anjar. We welcome you, sir, to the panel, and we request Mr. Darshan to escort him to the stage and welcome him to the bouquet. Welcome, sir. Next, we have with us Mr. Naveen Ahlawat, sir. Naveen, sir, is the Chief Procurement Officer and Head of Green Hydrogen and Gasification Projects at Jindal Steel and Power Limited. He is spearheading various gasification projects and green hydrogen projects, an essential step towards green steel at his organization. He is an IIM Calcutta alumni. He has handled projects worth $1.2 billion at his organizations. We are so lucky to have him as our panelist, and I request him to join us on stage, and I request Darshan to step in and welcome him. Next in the panel, we have Professor Vishwanathan, N.N. Vishwanathan sir. He is the head of department of Metallurgical and Materials Science. It is evident that Sir is our sole supporter for this event, and he has supported us immensely. So Professor Vishwanathan's research interests include process metallurgy and steel making. He has over 25 years of experience in steel making processes. He has been a part of Steel Research International Germany. Professor Vishwanathan has multiple time recipient of Excellence in Teaching Award at IIT Bombay. He has also served as a visiting professor at Royal Institute of Technology, Sweden. We welcome him on stage. So, to begin our discussion, I would like to welcome Mr. Gajraj Singh Rathore sir for his presentation and his opening remarks.
Good evening, everybody. I think it gives me immense pleasure. I don't know, when I looked at the clapping which Professor got, so I see that metallurgical department, very interesting and very popular looks like. Because when I did my engineering from NIT Trichy, way back in '85, not many students were coming forward to have this branch. We were 9 of us were there in that branch. And but I found it very interesting because I had made up my mind that I must do my engineering from this. So anyway, and now in the changing world, I was participating and as the audience in the previous discussion, and found that how the world is evolving, and probably it will go back and forth, because we all discussed that what is happening for every ton of CO2 which you produce, depending upon the process where you are in, whether blast furnace, converter route, or induction, or electrical arc furnace, or what kind of DRI you produce. Anything between 2 ton to 4 ton of CO2 is produced for every ton of steel produced. We in JSW, we are probably one of the company who always look forward for state-of-art technology, barring some acquisition which we have done, because that's a legacy which we have from companies which we have bought and acquired. And there also we are working very aggressively that we reduce this, because there are one plant having coal-based DRI, which is almost 4 ton of CO2 for every ton of steel produced, so which is very high. Within our, if I do benchmarking within our all 4 integrated steel plants which we have. So, but then back and forth, recently I was participating in one of the such discussion where, some Chinese colleagues were there. People asked them what is happening at the end of the discussion, what is your aggressive plan for CO2 and all that. So they were very, silent for a minute, and then they said, no, nothing happening. Basically today the time is to look for, securing energy for CO2. And you all must have seen that the thermal power plants which were closed in Europe and US, are coming back in operation because they are all struggling. You all know the reasons. Ukraine-Russia war probably has brought two things. One is it probably, time will tell, it has expedited the whole process of development which steel industry was looking forward for so many years. I am there in this industry for almost more than 3 decades. Not many development were coming in a quantum, I would say, breakthrough technology, which is required to achieve those kind of CO2 levels. And so probably this will expedite the whole process, or maybe for 1 or 2 years people will struggling to get rid of energy, security instead of talking about CO2. Probably they will forget for some time. But anyway, this is something which is bound to come. I mean, it has to happen. It's a matter of time. Probably after 6 months or 1 year, when things get settled, people, come back to the normalcy, and then there will be huge pressure for, environmental changes which are taking place. So I will just quickly take you through how it is happening in world. With these 3-4 slides, I thought I must talk about how the technology will evolve. Maybe this is our internal assessment of JSW Steel. I am not here to defend that converter or blast furnace route will do better or induction furnace will do better, because that's the technology and the fittest will survive. The bottom line is the fittest will survive, whether it is induction or electrical or anything. So with this, if I start, okay, so if you look at this, so if you look at this, I mean, these numbers may be vary from here and there. You can talk like in 2020, India is doing almost 108 million tons. The nameplate capacity is probably more than 130. So this is the distribution of the different routes of technology which is being used for producing steel. Almost 60 million through blast furnace, UF, then 25 is coal base, then NGDRI, EF 10 million, scrap 13, and this is how you come at 108 million. And what we see, how this technology will evolve, and finally, let's say by 70, which we all declared that we will become a carbon neutral by 2070. That's how I have taken. So by, let's say, at the certain CAGR which we grow, we should become a 540 million ton steel producer. And you see the blast furnace BOF, maybe it will sustain, because the blast furnace has also, trying to become more and more competitive, because I remember when I started my career doing pulverized coal injection, more than 120 or 100 would have been very good. And we used to be happy when we do 120, and we achieve 580, fuel rate, 600 fuel rate. We all used to be very happy. Now, within JSW Steel, we do more than 210 PCI injection, and our fuel rates are hovering around 520, 525. And our target is to go down to 480 in next 3 to 4 years. The PCI injection right up to, the system is being built to 240 kg. And there are many things which can immediately be done, because as far as Fe availability is coming down and down, more higher, low grade is being made available, high grade, iron ore is getting depleted, becoming more costly, which is making you unviable probably, or incompetitive, I would say. So beneficiation is one thing which is becoming a very important thing. One of the person I was talking, that a lot of water is required for beneficiation. He says that we are developing a lab stage. Probably this can be a project for IITians. They are developing a dry, without using a water, how can you, increase the Fe level through beneficiation, dry beneficiation for iron ore. That can be a challenge, probably you all should take and develop at a lab stage, and probably it can be commercialized. So this is how these different technology will grow. Then coal base, I think will get die, maybe sustained because of their survival, or they will somehow continue. Then then NG, natural gas-based DRI, EF will go, and probably this will also maybe sustain up to 15s, and then it has to come down. Scrap-based will increase because as more and more scrap is available. Today, in fact, within my company, we are trying to locate a land and put a scrap collection center, put a shredding thing, and probably it will come in operation in next 1 year. So that process has started. Still that somebody in the previous session was saying that in USA or in Europe people do this and that because still they throw their car within 3 years. But whereas we enjoy the car as old as the car is, we enjoy more, So 10 years, 15 years, so that mindset has to change. That is how this scrap circulation will start probably. And the scrap circulation, if you see, will keep on sustaining because that's the best way of producing steel. The CO2 generation, if you do that, and with hydrogen, probably it will be almost 0.1 or 0.2 ton of CO2 per ton of steel which you produce. It can be brought to that level through hydrogen route. Then, of course, that melting through electrolyzer, then this hydrogen-based here, that will go right up to 215 million ton out of 540. So that's the breakup which we think it's going to happen, and that's how this technology will evolve. And I just trying to put how these I've just selected 4 areas where how they will taper down. If you look at the first one, as I said, by 2040, that will peak, that route of technology which will produce steel will peak up at 40 and start tapering down, and slowly get converted through, carbon capture, CO2 capturing and utilization of storage. So it will peak at 120, and it will the other converter blast furnace route will start getting tapered down, and then similarly DRI, EF, today with coal, then NG, and then finally with hydrogen, it will have almost 6 times growth and go right up to 15. Similarly, the scrap route will go slowly keep growing as the more and more scrap is available. And finally, this is something which is being done at a lab stage, not very commercialized, but probably it will happen. And that is how this technology, through making, the oxygen at one anode and the cathode will have the iron, something like that. This kind of, maybe how far it gets commercialized, but somehow some quantity will come out of this route. And then, how this is probably a repetition but then I'm talking here about the cost also. So, how this contribution of net zero technology, you will have almost 25% coming to scrap route, then this come down to 22%. You see that will peak in 2030, almost 55% route, and then start coming down to 22%. And scrap route 25%, then the biggest contribution will come from hydrogen-based DRI and EF, electric arc furnace, to 40%. And if you look at the cost, these assumptions of cost are the hydrogen cost should come down to almost $1.5 to $2 for every kg of hydrogen we produce. That's the assumption. And similarly, CCUS should cost around $20. These are the assumptions. Today, hydrogen is almost 4 times costly, which doesn't make, you need to produce, for 1 ton of DRI, you need almost, 60 kg of hydrogen is required, and to produce 1 kg of hydrogen, you need 60 kilowatt. And then you have the Indians, electricity charges is 7 to 8 rupees or 9 rupees, I don't know what rates in different states, so you multiply. It's almost coming to 30,000 rupees for that hydrogen cost of production. So you can imagine. So today it is not viable. So the hydrogen rates have to come down at this rate, and then you will see that this different routes will have a cost of production, anything varying between $450 to $500 or $550, depending upon the prevailing rates. And Now for hydrogen, if you see today that hydrogen rates are, you see $5 to $6 or $7, and then slowly comes down to $1.5. And the blue hydrogen, you can see the line there, and the gray hydrogen. So that is how these rates by 2050, those will be probably will be the prevailing rates for cost of hydrogen. And you understand how much is hydrogen required. Almost 7.5 million ton of hydrogen is required to produce that steel. So that's the kind of production of hydrogen has to happen at those costs. So the technology has to get evolved. And just to, I think probably it is all information is public domain available. All you know, each process, produce how much of CO2 for every ton of steel being produced. So blast furnace converter route today is at 2.33 ton of CO2. Scrap based is lowest 0.66. So that's why everybody talks about scrap, but then availability is a challenge, and I could give this detail in the previous slide that probably it will touch 135 million ton out of 540. So these are the information all of you know. And just to summarize that, these are the four technology which is will prevail. Converter blast furnace, finally go to CO2 capturing route, because any company which wants to grow, I think in the previous panel again there was some discussion, for the blast furnace, because if you want to grow, I remember when JSW steel was the first million ton steel was produced in 1999, Corex technology, which we had a 0.8 million ton from one model, and another model came in 2002, 0.8. So let's say in 20 we were a 0.8 million ton company, and today in 2022 we are 27.5 million ton company. If we want to grow, and then of course no company in the world has grown at this pace. POSCO grew, they became 12 million ton in 12 years. Probably our growth is faster than POSCO. And if we wanted to grow in a normal route, I think we wouldn't have grown. Today we have a capsule of 5 million ton. A big blast furnace of 5,300 meter cube can do 4.5 million, and then you have a steel melt shop, 2 converters, 350 can do 7 million ton. Recently, the site at Dolby which we commissioned, we have 2 converters, 7 million ton it can produce, steel melt shop. A hot strip mill of 5 million, blast furnace of 4.5 million, a pellet plant of 7 million ton. Because that's the kind of scalability we'll have to work. And as you see rightly said that today we consume 74 kg of steel per capita, and the developed countries are at 300, 400, world average is 250, 300. So you can imagine the kind of the future which we have. Even in today's time, when there is a duty on export, so the steel industry is struggling for their survival. Probably Q1 and Q2 has been one of the bad years. I probably would say in last 3-4 years. And so everybody has to sell in domestic. You cannot afford to pay 30% export duty and still survive. So probably you have to be, I don't know at what cost of production has to be there. With today's iron ore and coal touching $300, $400. So I think it is difficult time, but again the fittest will survive. So the whole process of challenges which are coming is forcing us to do a bit of groundwork, start thinking way forward. Recently we have signed with SMS group of Germany. We will be spending almost 10,000 crore rupees for doing how we can work on carbon neutrality. And there are different routes. Like just to recap again, the blast furnace, our target is to come down to 400 kg of fuel rate, which we used to be at 600 some time. Now people are talking about, how things can evolve. I remember when fuel gases, which are there within the plant, like if I quote example of Vijayanagar, we do 600 megawatt power generation from the gases produced out of steel within, like whether it comes from LD gases or it comes from blast furnace or coke oven. Now the time has come that we have started thinking that, why do we do it, send it to power plant? We should inject into the DRI and we should inject into blast furnace. So DRI we are planning to go in Vijayanagar. Can we do 100% hydrogen injection? In Dolvi, we have calculated that without doing much of modification, we can pump 32,000 meter cube of hydrogen. So which will bring down my, cost almost by 2/3. 1/3 will be the saving. So that's the kind of NG, you all know NG rates today. They are all crossing, $20, 60, 70 rupees per kg of NG gases which is available. So the thought process has started. Now, how do I take spare COG, which is being used for power? So there is a massive plan in JSW Steel to go for renewable energy, make our all plants renewable based. We have already planned for Vijayanagar more than 850 megawatt power generation. 200 is already commissioned, another 600 will get commissioned in next 2 years. Similarly for Dolvi and other locations. So after going through renewable energy, the power coming from there, make all your gases spare and use COG and blast furnace for injecting into DRI and blast furnace. That's the kind of work which is happening. But there is another challenge that is it possible to switch over completely to renewable energy? Probably not. Because the wind energy which you have, you will not have all along the year, 12 months, that's not available. Solar energy, the government of India has already come out, I don't know whether it is the right platform to speak or not, but then there is a very adverse policy that you don't take from China. So the solar people, there is a slowdown in solar power coming out because people are finding it difficult to do at these rates. Somebody has to have some manufacturing units for panels and other facility for solar. So solar is a bit of taking a backseat. The wind is coming up. But again in solar, we all know that it's not available throughout the year. That's another challenge. Then in such a large plant where, if I quote an example of Vijayanagar where my requirement is almost 1000 megawatt for a 13 million ton as on today, islanding is very important. Suppose your power gets stripped. So we calculated that almost 300 megawatt is required to save my plant which has to run 24/7, 365 days. Like cocoa and batteries, I cannot shut. Blast furnace, I cannot stop just like that. My blower, which is a 45 megawatt power requirement for a blower, which is pumping almost 8,000 meter cube of air every minute, has to have a 45 megawatt. So likewise, if I calculate 300 megawatt islanding power is required. So is it possible? Now, then what is the solution? To have a banking, the banking of renewable energy. So that again, a lot of things are happening and you need a huge capital investment. So much of things are happening. So with this, I think I will close my presentation because we would like to hear more from you. You are all young people, can throw more lights and take more projects. As explained by Professor, that we have already signed an agreement with IIT Bombay recently to have and how we can work together. These were my thoughts, how the steel industry is going to evolve about and the kind of challenges which are there, which we all have to put our head together and try to find a solution. Thank you. Thank you very much.
insightful. It was filled with data and analysis. It gave us a wholesome view of all the different alternative technologies that are there and the economical aspect and also the growth opportunities that lies on those alternative technologies that are presently there to make green steel. I would now address this question to Professor Vishwanathan to explain us the technical aspects of all the emerging alternative technologies that are present to make green steel.
Yeah, thank you. So first of all, of course, I would like to thank and welcome both of you to, with your busy schedule to come for this particular function. And I also want to, both of them are from the Jindal group. I just want to tell you also that, when the Jindal JSW Vijayanagaram plant was first built, many of you may not know, it was the first MD was Dr. S.K. Gupta. And actually, he started his career at IIT Bombay. He was a professor at IIT Bombay. He was the head of the department. And then he moved to the corporate world and he built that old plant. And also I would like to tell you that IIT Bombay has recently signed a large collaborative engagement with JSW on different aspects, etc. So that way we will be contributing towards the steel growth in our country, and I know that JSW is playing a big role. Of course, we are also looking at similar things with other steel plants also. So with this, let me first say that my biases are always towards blast furnace. Okay. There is a technical reason for it, and of course personal reason that I have been working on blast furnace for a long time. So if you look at blast furnace per se, it has so many years, decades it has stood. The reason for that is two. One is, all of you know, technically we talk about, Carnot efficiency or thermodynamic efficiency. Blast furnace operates very close to this efficiency. That means if you are using the same fuel mix or whatever it is, no other process can be as efficient as blast furnace. Of course, at the same time, blast furnace also has evolved. There are alternate technology which has come, but blast furnace has always evolved, to those technology by adding some auxiliary fuels and all those things, and that is why you see that always when we talk about different processes, especially where iron ore reduction is involved, blast furnace still comes on the top. Okay. Just to show my bias towards blast furnace first, that's why. Of course, you have to look at blast furnace alone is what I am telling. But if you want to look at the whole steel plant as a whole, then, one may have other possibilities, and that is the way to look forward. So now, how do we look at, as far as Indian steel industries are concerned? Of course, we have two, the large integrated plants versus the small ones. So first, let me talk about the large ones. I feel technologically there can be three levels of opportunities. One is at the top level, where we have to look at the system as a whole. Just to give you one example, is from ISRO, where I was listening to one of their top managers, where they were talking about at the managerial level. See, steel plant is a large system or large number of shops involved, and at the end, the final product which is produced, the quality of that product depends on all these, different shops through which the whole process goes through. If you look at some 20, 25 years back when I was a student, at that time quite often there is a tendency to, if there is a problem in the product, which shop has created the issue. This was there at that time. I have heard from the operators and all those things. But if you, ISRO, for example, similar issues were there. Whenever there was a failure, somebody or other knew what was the reason for the failure, but still that did not come out for reasons because they don't want to come on the way of the whole project, or they thought it is small enough, or they were scared to tell. But ISRO changed this policy, and changing that, you look at everything as a whole, and if anybody comes with an issue, you look at in total, not in isolation. Why am I telling all those things is, of course, now with a lot of instrumentation, data is available, so much more information is available. So that was also Professor Asim Tiwari was talking about. So there is one way by looking at these data, we can look at the possibility of how to bring down, the energy efficiency, means increase the energy efficiency, or that also in a way will result in bringing down the carbon footprint. So that can be the first level of thing which can be done, which of course, data analysis and those kinds of things can do. Then the second level is, again, there may be a lot of energy which may be, which can be utilized within the, there may be a lot of heat because we do a lot of, heating things and all those things. How to utilize all those things? And it can be even chemical, there can be, heat can be recovered. So this can be the second level of doing things. Just to give you one more example how we can, looking at a process. If you look at a steel plant, quite often production is one of the very important parameters for them. But again, if you look at systems, products, when you try to produce more, the efficiency of the system comes down. This is also well known if you look at the system. And that is true for many of the systems or processes in steel plant also. But then there is also another thing which one needs to look at. If you try to produce more, there are also challenges in terms of anomalies. There will be disturbances which will be coming. And when these disturbances come, then one may need to intervene, and at that time the production can come down. Okay? So then one needs to look at these things also, and not only production comes down, but also your efficiency will come down because you may use more carbon to look at that problem. So maybe there may be an optimum production efficiency window, where if you try to do more, then also both efficiency as well as overall production, integrated production can be an issue. Of course, you don't want to produce less also because then it becomes a problem. So there can be a window. One needs to look for this window. So again, that needs to be looked at as a whole. And then I was telling you the second level is looking at the analysis and what all things can be to harvest whatever heat losses or all those things. That's the second level one can do. And also, as I told you, we can utilize. For example, I was talking about again blast furnace where we can utilize the lot of hydrogen is coming from coke oven gas. So almost 50% this hydrogen is there. So we can put those hydrogen or CO plus hydrogen into the blast furnace at the bottom, and then that can bring down the carbon emission. So these opportunities exist within whatever existing processes which is there available in the plant. And let me also tell you, we are having new blast furnaces which are built or which are being commissioned now, and once the blast furnace is put, at least 20 years minimum, 20 years it will continue. So that means we can only increase the process efficiency through these kinds of processes. So blast furnace is going to remain, I don't know, surely another 20, 25 years or even beyond that. Then, when it comes to, of course, if hydrogen becomes a reality, that means if this hydrogen has to be produced from green electricity, if the electricity is also green, all those questions are there. Okay? Then, of course, to reduce the iron ore, one can use, then the blast furnace will vanish. As far as carbon is there as far as you want to melt the iron in the furnace, blast furnace will remain. But otherwise, if you have 100% hydrogen, then DRI will be the norm. Probably that is what will happen when hydrogen becomes more and more. So DRI followed by, of course, electric arc furnace, because again to produce, hydrogen, you are using electricity. So there is a loss in efficiency. Remember, whenever we do energy conversion from one to another, there is a loss, So hence, instead of, you can straight away use the electricity, that way electric arc furnace DRI becomes the norm. So I believe that is the way probably the technology is going to evolve. So blast furnace will continue to at least 25 years, or beyond that it will remain so, till hydrogen becomes a reality. Okay. Now let me also talk about the other sector, which is the small sector, or not small sector, but small plants. Okay. One of the issues with India is we don't have, even in blast furnace or in other processes, we don't have coking coal, or rather even PCI which we inject, that is pulverized coal, most of it, 85% of it is being imported. So very good coal which can be, or the metallurgical grade of coal which can be used for our steel making plants are not really available in our country. So now utilizing this can be something which is very good for, but the problem is how can we utilize that? So if you look at the, the DRI production by rotary kiln, there is a large scope for improving their carbon footprint. That's what I believe so. Because there can be, one needs to look at this process more effectively, and, one needs to understand, because instrumentation, those things, still scope is there. So there is a large scope for improving the efficiency, that way carbon footprint will come down. And the other thing is, if we can utilize the Indian coal, which for example, I know that JSPL is trying to do, because it contains a lot of ash content. And then we can, using that coal, you generate gas. And that gas can be used to reduce the iron ore, so that, the ash doesn't go into the furnace. So ash can be got out through the, the gasifier plant. And also there are other byproducts which can be formed through this gasifier. So that seems to be a potential route, but there is also a problem of scaling. The rotary kilns, they are all, they can be, 100 tons per day, or maybe, 200, 300 tons per day. That is the capacity at which now the small scale operators operate. But if one needs to have a larger steel, using Indian coal, suppose one wants to produce gas and produce DRI and then melt in induction furnace or electric arc furnace, then the capacity of the plant has to be much higher. So possibly, in future what may happen is, now we have two players. One is the large integrated steel plant, and the second one is the small ones. Maybe we will have an intermediate player, possibly, where they may use a gasifier route and produce DRI, and probably this DRI will be transported to different locations. Because why induction furnaces is also there? Because markets are nearby. That is the issue. So hence, probably what will happen is there will be an intermediate player which will supply the DRI as well as scrap, because I don't think with the scrap alone we will be able to survive. If you want to, 74 kg, we want to go higher, we need to have more, iron ore to be, more iron to be produced from iron. So I believe that is probably could happen if you look at the scenario in the coming 25, 30 years. So that's what I believe will be the overall scenario from my perspective. Thank you.
Thank you so much, sir, for all the insightful and technical details. Since we are talking about gasification, I would like to take this opportunity and request Mr. Naveen Ahlawat sir to, since he is heading various gasification projects as JSPL, and JSPL has one of the largest gasification projects at Odisha. So what is the role of gasification in our future of Indian steel industry, and how is it as an essential step in steel making?
Hello. Thanks, Professor Strongman, for inviting and giving a platform actually to interact with the young brain, from the youngest brain of the actually finance institution in India. So thank you so much. So we talked about the basically how as a country per capita consumption, how it is so low, and what is our aim, how we want to be the such a high highest population actually. So how we want to increase this per capita. So first is to go on pushing, augmenting our steel capacity, which all of us are doing. The moment we start as a big player, small player, medium player start making money, we start augmenting the capacity to cater the needs of the country. So that is one way. Second is about how to basically deal with a demon of sustainability, reducing the carbon emissions, so which we all have to basically think and which we have to act actually. So now so the issue at hand is basically how we reduce the carbon footprints. The solution is not going to come overnight. The solution has to be a multi-pronged strategy, and it has to be a hybrid strategy which we all have to deploy. It cannot be a standalone strategy of going green hydrogen or going coal gasification route or scrap route. It has to be a combination of 2, 3, probably 4 strategies. So what at Jindal Steel Power, what we did actually, our former chairman, late Sri O.P. Jindal in 2004-5 actually, this is actually the vision what the person was having, at 2004-5, we started thinking that why we can't use our Swadeshi coal. The coal, wherein we have 472 billion tons of coal reserve. Out of that, 172 billion tons are recoverable. So for next 50 years, we don't have to think about second or third source, but we have to think about how we can utilize, monetize our Swadeshi coal. So the technology was seen, how we can gasify this coal. And our plant, one of our plant actually, which is actually a flagship plant right now, it is in the state of Odisha, in Angul, where we are gasifying coal. We are right at the pit head of the coal. But again, this is the bad coal. India has got the worst coal available in the India. Actually in the world, sorry. So why it is bad? It is bad because of a couple of things. First, it has got the highest ash percentage, which is close to 45%. So most of your energy just go into just to extract ash and just getting ash out of the gasifier. So that is point number 1. Point number 2 is about the ash fusion temperature. The ash fusion temperature is close to 50 degrees centigrade, which is also pretty high. So there are few technologies which are available, which we have to sort of capitalize, which we have to see that how best we can sort of use that. So we zeroed on to the Lurgi technology, which is actually now the air liquid technology. We started with a noble mind that yes, let's start with the 2 million tons per annum of DRI, coal gasification based DRI facility. And again, you can just think about it, a steel manufacturer taking a plunge into a petrochemical kind of a plant, which is actually newest of the plant altogether. So we struggled a lot, starting, how to really put this plant into place. But then yes, getting all the PMCs, finally this plant was commissioned in 2014. And as we speak, the plant, we are running it successfully. So now, there are some issues here. The issue first is the highest ash content, as I said. That is the issue we have. Second is about the size of the coal. The size of the coal has to be 5 to 50 mm, which actually then we have to deal with the fines. So then those fines, instead of using in the gasifiers, we have to use those fines in our power plant. So that is our point number 2. Issue number 2. And third is about the advantage we have. The advantage actually is basically on the reduction in the carbon footprint. So this route, we believe, coupled with the utilization, carbon capture utilization can be the future strategy for India to actually go with this transition. Till the time when the hydrogen cost will come down to 1.5 to $2, what Rathore Sahab has just shown in the presentation. Right now it is hovering around $4 to $5 per kg, and with that the cost is coming around $450 per ton. And $450 per ton we are selling our steel, right? So it is probably not possible. But we can harness the coal we have, and that is exactly what we try to do. And we are running these gasifiers successfully in Angul, making DRI, highest quality DRI. Metallization is close to, total metallization is close to 90-92%, and we believe that it can be further improved. We have our plans as we speak for next couple of modules. We are going ahead with coal gasification route. We are contemplating about the different technology, the pain point we have in our existing Nurgi technology, how we can plug it by actually exploring the different technology like entrained gasifiers, wherein which can utilize fines, which can give us low methane percentage, and wherein we can increase the productivity of our furnace. So this is what we are doing, and a lot of challenges are there. Like I'm representing my company in Ministry of Steel, and we are talking about Professor Green Steel. We are not clear what is green steel, right? Like US, they have the different definition of green steel. We have our different definition of green steel. So first, we are struggling with a lot of confusions and questions. So I think those things, till the time we struggle and we come out with a final solution, I think this transit zone where we can actually harness the energy, this is what we believe can be a good way. First. Second is about to really capitalize on the low-hanging fruits. So as Rathore Sahab has said that coke and gas has got 58% of hydrogen, right? So that hydrogen, with the help of, you can purify it with the help of precipitation adsorption, and you can use that hydrogen at least to start with. So see, because 100% hydrogen, this technology still need to be seen. There is a plant in Sweden, in Stockholm, Green Steel, the name of Green Steel. They are putting a plant of 3 billion tons per annum. Probably this plant will come somewhere around 2026, and they are going to utilize 100% hydrogen. So there are question marks on the technology, because if the reaction is 100% endothermic, we also need carbon in the steel. So how we are going to inject it? So there are issues about the temperature, about the productivity, how it is going to happen. So that is also a point that we can see. So according to me, I firmly believe that we should focus on the quick wins we have, and there are quick wins available. Coke gas is the first molecule which we can harness, the easiest way to go, and we have already started doing it in our Angul plant, wherein we are using 15 to 20,000 normal meter cube per hour of coke gas and injecting into the DRI furnace. So that is the first thing what we are doing. Second is about the use of synthesis gas. Synthesis gas also, it has got close to 53% is hydrogen. That can also be with a shift reaction. It can also be converted into hydrogen, and then hydrogen can also be used. Now, that is basically how Rathore Sahab just touched this point about how we go from waste to wealth. So that is a new thing that is going on, how to go with waste to wealth. So it is, now every molecule, every gas molecule in the integrated plant, we are thinking, okay, can we have carbon monoxide into this? Can we have hydrogen into it? And how we can use these two, molecules just to make maybe downstream chemicals, or to use these molecules to make, how to reduce it in DRI. Because this is very important. Using this gas as power, as a fuel, I think it is not good. It is absolutely tantamount to crime. That is what I believe. We should harness it, we try to monetize it, so that we make downstream chemicals like bioethanol, methanol, and go biological route. We can make biomass. We are short of algae biomass. In India, we maximize our food habits are more toward carbohydrates, right? And if you go in the countries like Taiwan or Japan and Thailand or Malaysia, their intake is more on protein. So there is a huge demand of this algae biomass, which is crude algae oil. So just to give you the economics, the cost of production of crude algae oil is close to $600 a ton, and the selling price is mind-boggling, $5,000 per ton. Right? That is what the current market price of this item is. So there are some low-hanging fruit which we should focus, and that is how we should transit in the next 5-6 years. Till this time, this green technologies like green hydrogen, green ammonia, green methanol mature, or at least come to a technical readiness level of 8 to 9. Until by that time, I think we can see a lot of disruption happening every day, every week, and at the right time, we should just take our plunge. Thank you so much.
Thank you so much, sir. I believe, sir, Naveen sir has rightly pointed out some very interesting facts. First being that while producing grey steel, we are directly jumping into the question of green steel and forgetting the intermediaries that are also there. So I open this question to the panel, and maybe someone can take this question as to where are we in the line when we talk about grey to blue or finally to green steel? Where do we lie as Indian steel industry?
No, I think this is already explained probably in my presentation. It's a repeat this thing, but I can just repeat again. See, as we said that, and he also explained just now, that one is blast furnace and DRI. These are the two routes where we have to bring down the carbon. Now, how do we bring down the carbon? So, blue means using NG without storage, CCSU, and grey is not using the storage, not recapturing the CO2. These are the two difference between blue and grey. So again, the technology had to evolve. I mean, saying that tomorrow we start capturing CO2, it's still in a very niche stage and the developing stage. I think day before, yes, a few days back, probably I was having a discussion with a company called Toyo. They have a large engineering company in India. They are probably worked with a lot of chemical industry where a lot of storages are being created. So they are also still, a lot of discussion only happening. Because at the end of the day, there is a business to run and make some money. If you have money, then you invest. So, but the good thing is that the thought process has started, people have started spending, as you rightly said, low-hanging fruit is what? Syngas, which you can again inject in blast furnace, and there are two ways of injecting into blast furnace. One is through the tubers, but then there is a limitation. You have to have a dual lancing, so you can inject PCI and you can inject COD or NG. And then you have above the vessel, you have again create a similar kind of system above the vessel, and you have the total completely different set, the way you are injecting, PCI. So the repeat one you can have, and all both put together, probably you can bring down the coal consumption by 80 kg to 100 kg. So today when I said 525 kg fuel rate for a blast furnace, by improving the FP, by doing more and more beneficiation, more and more plants are going for beneficiation, so that's one route. So if you bring down your slag rate, because one of the plant in Tata, that's Huguman, they do 440 kg of PCI injection. They have been doing for years together. Their slag rates were 220 kg. So it's easier to do. Then today we are touching almost 210 kg with a slag rate of 360 to 380. So that's a big achievement for the Indian company, because we always used to look at the Huguman plant, they are doing 240 kg with slag rate 220, which will never be available in India because that kind of iron ore is not available. But I think our achievements are larger than, I would say, Huguman, because we are doing 360, 380 kg slag rate 210. So I probably feel that this is more, challenging one. So similarly, now people have started, we said that in JSPL they are doing almost 14,000-15,000 COG injection in the year. So these are the routes of immediately being done. And carbon CO2 capturing will take some time. You are doing on a smaller scale, 10 ton or so, but you see if you burn 1 ton of coal, you produce 3.2 ton of CO2. You imagine. And I think for blast furnace, 600 kg for the complete steel making, I would say 600 kg of coal is required. Like you need 1.8 times of iron ore for every ton of steel produced. Similarly, you need 600 to 700 kg of coal for every ton of steel you produce. So imagine the kind of CO2 which is being generated. So capturing that CO2, converting into methanol or ethanol, and then storage. Today, India is a net importer of methanol, and there's a huge opportunity. But then, need to have technology, you need to have capital investments. So things will get evolved with time. I think probably the situation has forced us to expedite the whole process. Nobody was talking about, this environmental challenges, but time it takes care of everybody. So the situation is getting created to expedite the whole process, and I think, as the Professor said, that they are ready to take challenges. In fact, when he was talking about blast furnace, there were a lot of problems which was coming to my mind. And you are fond of or you are lover of blast furnace, but the blast furnace is a black box. You don't know what is happening. Though a lot of level 2 automation had got developed. I mean, you can predict. We have a technical tie-up with JFE. They have a 33 million ton steel plant in Japan. One of the blast furnace challenges is that when you have a poor quality of something going inside, like the prepared button like pallet center and ore which you are charging, something goes wrong, more fines goes inside or moisture goes inside. You don't know when the problem will start inside the blast furnace. The slippage will happen, 2 meter, 3 meter, the slip will happen, the burden will slip, and the blast furnace will go to the chiller side. In fact, one of the assignments which I was thinking that if you can predict what is happening inside, and there are people who have developed this. I'm not talking something which is required to be developed first time. But see, the technology transfer takes, nobody gives you free of cost. And that's what the European and Japanese, they have reached a level of maturity that the technology which they developed 20, 30 years back, they have started selling to us. And it costs big money. So my suggestion, and probably we already have a tie-up, why don't we take such mathematical model development for blast furnace, for TRI, probably it will be cheaper. Then there's no point in paying to Japanese and European and foreign exchange going out. So there are a lot of challenges as of today even, and we can bring more reliability and sustainability. And if the process is more sustainable and reliable, 10%, 20% rejection, 10 to 15% improvement in terms of fuel efficiency, in terms of cost can immediately come. So I think we should take that challenge. And similar in the case of DRI. And these are the two big contributors, because today there's one more discussion happening in the world. People are talking to replace this blast furnace altogether. In the sense, maybe the scalability and commercial thing, and blast furnace can go to 4.5 million, so how big that can go, that you have a DRI, and DRI, single DRI feeding two open bar furnaces, where you keep on continuously adding DRI. It's like a submerged R furnace. It's a mix of submerged R and blast furnace. And if it gets commercialized successful, then you have a replacement of blast furnace. Thank you.
About the blue, I think this is the right, we are in the right actually spot in terms of, to capitalize this. So, see, capturing CO2 is not a big issue. It's a proven technology. Whether you can do it with a physical absorption, you can do it with a chemical absorption, there are ways. But then, once you absorb it, how you utilize it, that utilization is the biggest issue right now. So as we speak, in our plant in Angul, we are capturing 2,000 tons of CO2. So via physical absorption, 75 tons per hour, and via chemical absorption, 75 tons per hour. 150 tons per hour we are capturing, and the concentration of CO2 is as high as 95% plus, which is actually ready to be utilized to make methanol or ethanol or soda ash or biological LV, or maybe to use as a enhanced oil recovery. Right? So it is absolutely ready to use, but then utilization is where I think the most of the time is going to come where how we are going to sort of scale up this technology. So we are thinking about so many things, and Dr. rightly said, methanol is I think a low-hanging fruit for us. Methanol, India imports close to 1.2 million tons of methanol every year. And with methanol being as a basic feedstock for so many chemicals, downstream chemicals, and in days to come, methanol can be one of the few which will be used as, to be used as a blending fuel along with petrol, and it will also be used as a fuel in bulkering in ships. So I think this is a good chemical which can be produced via CO2. And so these are the things. So I think utilization is a challenge at this point of time. Even there are a couple of plants available in the world which are actually doing it, but they are doing it at the level of only 400 to 500 tons per day of CO2 utilization, which is very small. So I think we need to see the scale up of this technology, maturity of this technology, and then I think we have an answer once we know how to utilize it.
Just answer to what Mr. Rathore was talking about. As far as blast furnace modeling is concerned, we have a very good model which we have developed in partnership with Tata Steel and Tri-Diagonal, a CFD-based company, on a platform called OpenForm, which is as good as, for example, I will say Bright, which is developed by Japanese, and there is also another one by Europe, and forgetting the name. Rather, I will say much better than that, because we have used some of the latest things which are available in CFD, which is available in OpenForm. And to extend it further, of course, that kind of a model can be used for understanding different scenarios and all those things, but always plans, the furnaces don't operate in a smooth fashion, as Mr. Rathore was talking about, where there are always some anomalies happening. So for that also, if you look at, we are talking about artificial intelligence and all those things. If you look at the literature, the first artificial intelligence was actually applied in blast furnace by Japanese. So there are so much data, which is coming from walls of the furnace. There are heat flux, there are pressure probes. Using all those things, there are ways to know early enough, and that's exactly the point. We can know early enough there is a problem which is going to happen. Even that is used in continuous casting, for example, extensively. Similar thing can be used so that we can, if we know the problem early, then we can take a corrective action much early, and also it will be, the corrective action will be much smaller, because once the problem becomes bigger, then the corrective action also will become bigger. So all these things results in efficiency, production, all those things will happen. And coming to what we can contribute towards hydrogen in that respect, again with respect to processes, one of the challenges which will come when it comes to hydrogen is, we know that, as he also pointed out, that hydrogen, if you use hydrogen, it is more endothermic compared to carbon monoxide. And so we need, if you heat the gas more, then there are other problems in DRI. The DRI will stick to each other and coming out. There are, these problems are there. So, and there is a whole system, The hydrogen has to be heated, then it has to be heated, and then you have to condense the water. You cannot utilize the hydrogen 100% because of thermodynamic reasons. Then you have to bring back the hydrogen again and heat it. So there are a lot of cycling which goes on. And these things, for example, can be very easily studied using such simulators. which can be used for the existing DRI reactors because you just have to mix CO and H2. And to a large extent, we know kinetics. At the laboratory scale, rather we use hydrogen rather than carbon monoxide because laboratory carbon monoxide is, it's poisonous. So in a student environment, we do most of the studies using hydrogen rather than carbon monoxide. To a large extent, we know the kinetics or some of the fundamental aspects of ion reduction as far as hydrogen is concerned. So once we build these kinds of simulators, which can be useful for the existing DRI plants to improve their efficiency, which we are capable of, as well as we can also use for the future scenario where, if you increase more and more hydrogen, how the process needs to be fine-tuned. Some of these things can be very well studied so that your experimentation, window can be brought down wherever, whether it is pilot plant or at the plant scale.
Thank you so much, sir. So with these discussions, it is pretty evident that Indian steel industry as a whole is taking aggressive measures to decarbonize the steel industry. But we are still a long way ahead to achieve 100% green steel. There are various technological interventions that are required. There are serious bottlenecks that needs to be addressed. And we as the Premium Research Institute should be focused on, inventing and researching more about this topic. So I would also like to take this opportunity to focus things on the policy side. So since we have two industry leaders here, so I would like to have their thoughts on what kind of government policies are required to make this push happen. Because any sort of technical interventions, when they are needed, there is also a government push that is needed to make them more commercial and get a wide acceptance in the industry. So I would like to ask what policies are needed and what policies are already in place, and such as talking about carbon credits or green bonds. What regulatory challenges do they face and how will they impact the industry?
So let me start. So first, the intervention. One thing I want to tell you is that government of India is taking this thing very seriously. As we speak, every fortnightly there is a meeting the review meeting that is going on at the Ministry of Steel. So a couple of things need to be addressed. The government is going to address with the policies which are going to come in next, I think. First is, as I said, definition of green steel. What exactly do you mean by green steel? Second, the demand center. The demand side of the where this green steel, I will make green steel. Who will buy it? At what price they will buy it? So creation of the demand center, that is important, and that's why government of India has to talk to our customers like the automobile industry. What kind of provision, what the possible green steel they are going to buy. Number three, the pricing of the green steel. Now see, we have to understand this green steel, it is going to come at a premium. It is not going to come below what we are producing right now. So there is a premium that is attached to it. So if my customer is not willing to give the premium, or if I am not able to recover my cost, up to certain level we can do that, but beyond that there is no business without if we are giving money from your pocket. So that need to be fixed, right? Fourth is on the utilization side. I touched upon that the government of India with the help of PLI schemes or the viability gap funding, they need to basically all these products are going to come at a premium. The production or the technologies are at a nascent stage, and the government of India has to basically bring in this viability gap funding to make these utilization technologies possible, or at least we can start at least in the semi-commercial level. So I think that is the third one, and the fourth one, of course, is the awareness, which I think all of us, I can tell you with full confidence that across the globe. In India, the kind of awareness we have for the carbon emissions, the carbon intensity, the green steel, the sustainability, I think it is way higher than our global colleague, and we are right at the cusp of the progress. I think we are on the right path. In next couple of years, I think the way our transition will be, it will be at least 5 to 6 times higher than what our global police are doing. So I think we are on the right track. It is just a matter of support, intervention from the government side, and we as a professional and academia, where we can join hands and we can work on this technology which are at the lab stage. If you can take it to a semi-commercial, commercial level, I think we can do wonders. Thank you.
No, I think he has already covered. Probably I will say last thing that the government of India was the level playing field, in the sense that if we are left, we Indian steel industries are giving tough time to our competitors today. Probably that is the thing which will make, don't put duty on exports, so that itself killing the market. And if you level playing field in the sense, the way you all see how Chinese steel industry is being supported by their government of China, or American, probably they talk big, but probably I would say in the world the American market is most protected market in terms of the steel which was sold all over the world at $900 per ton. In US it was sold at $1,800 per ton. Can you believe? So they are probably the most protected country. So I think he was also saying induction people should be given level playing field. So steel industry should be given level playing field. Rest all we can achieve along with all of you. I mean, we Indians we do wonders when we go out. Why we cannot do wonder when we stay in India?
I just want to add a point, of course, government policy, etc. But beyond that, just to give you one example, we generate so much plastic waste in Mumbai, and that is all dumped everywhere. Now, ideally, this plastic waste, if segregated, can be utilized completely, instead of going to the soil as, environmental hazard. It can be used by one blast furnace which is sitting in Dolly. Okay, that is the amount of production we are talking about. But what is the problem there? It is not the technology we can inject. Means some fine tuning and all those things need to be there. But I am not saying that. But the more challenge is, as citizen, are we responsible enough? See, the problem is we don't segregate. See, why it happens in Sweden is because as citizen, everyone is doing that segregation. See, that is the cost which is we are not able to do. So, in some sense, I don't know, government has to bring these kinds of policy, and also as citizen, we need to work on those things so that these things become usable, can be, either recycled, or when it is cannot be recycled, it can be burnt properly by whether it is cement industry or steel industry, and that can really bring down a lot of our waste, as well as it can bring down the carbon emission. So in a way, there is large role as citizen we also need to play.
Thank you so much, sir. So, in this entire discussion, we have come across various facts, figures, and data. And after techno-economic comparisons of the various alternative technologies present, we could see that the two emerging technologies were BF-BOF with CCUS technology, and another was DRI-EAF along with using H2O. Am I right, sir? Yes. So, we as an institute, we have a responsibility to create awareness and work towards this so that we can decarbonize one of the major carbon polluting, like carbon emitting industry, that is the steel industry, and hopefully work on the following set alternatives and achieve our goal. So I would just request the panelists to give their concluding remarks before we end the discussion.
I think we have talked a lot about technology. I think the world looks very exciting as far as I feel personally. the steel industry in particular. I don't know how about you. How many of you, look forward for these kind of challenges? And probably what I say is, I have been there in this industry for almost 3 decades, 32 years. The kind of thing which is going to happen in next 5 to 10 years, the breakthrough technology development, or probably didn't happen for last so many years. So the steel industry, I would say, is very exciting, and I will request IITians and professors that they should spend for this transformation which is going to take place. They should pick up more and more projects, tie up with the industries. We also, the industry is ready to come forward. I think one of the good things in overseas, when I travel, most of the steel plants, they have a good tie-up with either one of the university or academia or college, and they work very closely. Of course, here the both sides are responsible, because typically the Indian steel industry, or every industry for that purpose, or totally the Indian mindset, don't spend money on the R&D, because the kind of budget allocation which probably we do is very low, and because then we feel that there are more priorities, spending money, and we think why to reinvent the wheel. When something is else happening, copy that, and then these were the kind of challenges. But now we are no more. We are probably the second, third largest steel producer. The way we are growing, I would say, in this tough time, the only light and hope is Indian steel industry. Europe and everybody, even China, has come down to level of 3.5% GDP. They are talking next quarter 6 GDP. They say that they will do, but I don't know how they will do. Probably they are the lowest, and we are fast growing. As far as steel growth is concerned, it's almost growing at the rate of 5 to 6. No country in the world is growing at that pace. So we have a bright future. I think it's right time probably to come together and make this country better. Thank you.
Just to add about what we are capable of in terms of innovation, etc. Yes, we are capable, but where are we lacking? See, one is of course academic level. We can generate ideas. We can test these things at the laboratory levels. But what we lack to a large extent, I believe, which we have also told this to Ministry of Steel, is the engineering as well as pilot plant expertise. It is a pilot plant, plus it also needs an expertise which is not just research expertise. What we have is research expertise, but something to convert an idea into a pilot and then to a plant. It needs also an engineering expertise. This to a large extent, I don't think we may have here and there, but I think that needs to be consolidated. I believe so. And the other thing, which is needed, is also to bring this pilot plant or engineering expertise. The different steel companies have to constructively collaborate. That means, again, if you look at Europe or Japan, some of these countries, what they do is they, to a particular TRL level, they collaborate, and then, especially I'm talking about pilot and those scales, and then once it come to a beyond a particular TRL level, then maybe one of the companies get interested. They would like to develop it further. And that kind of opportunities we need to create, then only, we'll be able to innovate and create an, environment which is also, so see the problem with this, when we have technology from outside, we have our own iron ore, which is very different from what, that is why we are not able to produce their productivity, because we are alumina content is high. So there are issues. So we can have our own technology, and we can also, not only in production, we are the second largest, but also in innovations, we can become leaders if this particular gap is filled. And I think we need to do that.
first point has been properly done, that the interface, the hand holding between the academia and the industry, that need to be strengthened. Yes, I think today when we are seeing so much of disruption, this is the time where I think जब मुसीबत आती है तो सब यही बोलते हैं यार चलो यार अभी तो हाथ मिलाते हैं तो डूबेंगे दोनों. So I think that this kind of disruption which we are seeing on daily basis, I think this is the right time when we both industry and academia should join hand, and that is what we are doing, because there are so many things. I like from my company, in last 2 odd months I have visited close to 9 odd issues in India, including National Chemical Laboratory, IIT Roorkee, IIT Bombay, IIT Delhi, IIT BHU, and you name the issues. Indian Institute of Science, Jawaharlal Nehru Institute of Advanced Research, and everyone, they are doing a fabulous work. And the kind of work which these issues are doing, we at our industry, we don't know what they are doing, right? And there are some challenging, intriguing questions which they are trying to solve at the laboratory level, right? So I think if we can just sort of accelerate that hand holding, then I think we'll be able to crack that. So this is very important. Second, I also take this opportunity, at this platform, I would like to invite you all at least come and visit the plant. This is very important because theoretically you guys are challenging, you can solve any sort of issues. But then, seeing is believing. You must make it a point. I invite you all to see our, world-class facilities in Angul, in Raigad, all our plants. You must come. You must see. We'll organize everything. You must come, and because when you see it, then only you will be able to see that. Okay, you will bring that interest, in solving the issues, in metallurgical issues, in blast furnace, in DRI. Then only you will be able to crack it. Third, I think. It is a time when the core sectors like steel industry, you as a metallurgist, young metallurgist who are doing MTech or BTech or PhD, you should go into the core sector. This is very, very important, because if we have to make India Atmanirbhar, how will we make Atmanirbhar? We can't, get Japanese and make we can make Atmanirbhar. We need Indians, right, to make ourselves Atmanirbhar. So I request you all, please come join hands. Join hardcore industries. Just basically work on the shifts, work in shifts. Try to see what is happening on the ground. Then only we'll be able to see it clearly. Because I strongly believe that India is at the cusp of progress. Next, not decade, the century belongs to India. That is what I believe, and together we can do wonders. Thank you so much.
With these encouraging and interesting remarks, I now open the floor for some quick questions, if anyone wants to ask a question. Professor Vishwanathan had some urgent work, so he had to leave. So, any questions from the audience? Yes.
There will be a massive improvement. JSW has already tied up, and we are also in talk with IIT Bombay, and probably in next couple of weeks we'll try to converge. And see, I can tell you one thing: the kind of interest or the kind of disruption that is happening in the market. You don't have to wait for the internship. People will come and take you, right? So there will be the base level, as you rightly said, it is so low that you will see a huge jump in terms of. And internship part, see, we have already spoken to Professor Vishwanathan, and we have already extended our arm that please come, and there will be series of projects we can do together. So don't worry about it. Companies will be behind you. Don't worry.
Any questions?
Good evening, sir. Sir, I have two questions. I would like to ask two questions. First question is that the composition of carbon in steel, like what I have written, it is 0.04%. Like it varies from different steels, like varieties of steels. But I just wanted to ask that in the blast furnace, where you use carbon as a source of fuel to maintain the temperature, then how do you overcome this problem of setting the value of percentage of carbon in that accurately to the percentage which is needed, like 0.04%?
No, see, in blast furnace or that particular for any steel in iron making, you will have Fe close to 94.5%. And carbon varies, is around 4%, plus minus 0.3. And rest all are impurities. So the heat which is required, that is how the fuel rates are calculated. There are mathematical models available how you maintain, because the hot metal, the temperatures are maintained at 1500 plus minus 20 degrees. And how do you control your fuel rate? Again, I think we were talking about one of the mathematical models which I was mentioning, trying to see that blast furnace in the black box is a eta CO, which is the CO utilization, which is as if it is more higher, I mean if it is close to, I remember in my early days of career, the eta CO used to be 40%, 41. That is the utilization of CO, which is a reducer, convert from FeO, Fe2O3, Fe3O4 and all to FeO. So now there are level 2 mathematical models available. There are distribution from the top where the burden is getting distributed in terms of cylinder pallet and flux and spoke. That eta CO used to be 40, 41, 42. Today we operate at the rate of 49, 50%. This is probably 51 is the maximum as of today which is possible. So that is how you increase the gas utilization, you bring down the fuel rate, and you are able to achieve the temperature which is required to stay in the 20 degree. And that is how you achieve the safety and carbon.
Thank you, sir. That was a very valuable answer.
But I will throw a challenge again, I will repeat again, that I don't know what kind of mathematical model which is developed, Tata Steel, blast furnace steel is a big black box in the sense that, how do you maintain carbon manganese ratio, manganese silicon ratio, sulfur silicon ratio, sulfur manganese ratio, when the hot metal is coming out, what should be the right ratio which in turn will predict what is going on inside. This is probably one of the, in fact we are also trying to develop some data and see what is the best. You people should work on that. When disturbance is going to happen in blast furnace, when the slip will start, the burden suddenly will slip. The bottom zone, half, and that is how the pyramid is made within the blast furnace. All of you must have seen the blast furnace. So that the prediction should come when there is going to be disturbance in the blast furnace. These are the two challenges which all of you should take, and I think this is a good model to commercialize it, make some money out of it. Don't leave it to one. Today, Japan and these countries, the people have started making big money out of this technical development which they have done. But of course, it has to be sellable. Welding machine. Sorry, I think I will not be able to. Welding machine, see, I don't know, welding machines are used as far as steel industry is concerned. It is being used for downstream facility where the cold rolled products, where there are continuous lines like tandem mills, PLTC, pickling and tandem mill where the tail end of the previous coil is welded with the head end of the coming coil. That is what kind of welding you are talking about? Yes, sir. Yeah, but they are laser welders. Because see, those coils get finished within 3 minutes. 3 minutes, one coil gets finished, which is almost, I would say, 1,000 meters long. The speed which it runs, the mill runs at 1,500 meters per minute. So the welding has to happen within 1 minute. So the total and finish of the previous coil, the start of the coil is only, fraction of seconds. You don't get more than 30 seconds because you have the loopers which get filled up and you weld and the coil starts. So there are German companies, probably they have mastered it. So MEMS is one company, SMS, they have laser welders. So that ensures the guaranteed quality. So the thickness starts, it's a variation of thickness and the width also varies. The width starts from 900 millimeter to 2 meter wide. That kind of product variation comes. The thickness as low as 1.6 millimeter to 5 millimeter. So one welding machine has to take and then variety of steel. You will have low carbon like IF steel which you make for auto industry, as low as in ppm level, 15, 20 ppm carbon level. Nitrogen is less than 25 ppm. And then you have medium carbon where carbon is 0.35, 0.45 and then you have high carbon. And then you have silicon steel, CRGO, non-grain oriented. So that's the kind of variety one mill has to handle. So you really need a good quality because nobody in India is able to make that kind of welding machine as well today. It's all being imported.
Sorry. See, our position is good. We have to just see the technology is very simple. You have to just break water into hydrogen and oxygen. Right? Where is the issue? The issue is about the economics. The issue is about power. So to make 1 kg of hydrogen, right? To make 1 kg of hydrogen, 70% of the cost it goes in for power. So the power right now, power tariff is around 4.5 to 5 rupees, right? To sometime it is 6 rupees. So with that tariff, the cost of hydrogen will come somewhere around $6.5 per kg, right? So that is where the issue is. So as we advance the technology, the solar panels, which Mr. Rathore has just said, we enhance this production of panels, we reduce the landed cost of power. Then I think we will be able to, reduce the cost. That is the only way. The 70% of the cost is this. 20-25% of the cost is about the capex of the electrolyzers. Electrolyzers, yes, they are in 5 megawatt, 6 megawatt, 7.5 megawatt. From megawatt to gigawatt, they will also transit in next to 6 to 7 odd years. They will also mature in terms of technology level. But the major factor is about the power, right? So that is where we are, I think, and we have mining, we have crossed that path, in terms of reducing the price of solar from 6.5, 7 rupees to now 2 rupees, 2.5 rupees. So I think in days and in months to come, we will be able to optimize the power cost and so as on the electrolyzer cost. Yeah, so that is sustainable aviation fuel, SAF. So it is hydrogen is one of the way to do it. There are other ways like with the help of CO2, you can make basically methanol, and that they can use as sustainable aviation fuel. So that is also one of the ways to do it. Yes. So how to do that is the biological way. First you capture the CO2, then convert that CO2 into the crude, basically biomass, algae biomass, and from algae biomass you extract that and convert it to crude algae oil. And that crude algae oil goes into the biorefineries of companies like Shell, Exxon, BP, Chevron, and they already started it.
Power cost has to come down to have a hydrogen cost of $1.50 to $2 per kg. The power cost, which is 70%, has to come down to 2 rupees 35 cents, 2 rupees 10 paisa. Then it makes viable. Pardon? Yes, solar power, I mean, today the renewable cost, see, it is slowly coming down. The capital cost is also there, distribution cost, it has to go into the grid. The government will charge the duty anyway, 1 rupee 20 paisa duty. See, everything has to get involved. The putting 1 megawatt of solar or wind used to cost around 7 to 8 crore rupees for capital investment for every megawatt power generation. Today it has come down to 4.5. Slowly it is coming down. So the capital investment has to come down, the distribution has to come down. There is a business to survive, you need a bottom line for everything. We need people like you who will have a big breakthrough technology to make sure that it comes down to that level.
Power, then we are through.
So with this, I think we have reached the end of this panel discussion. So as this event now draws close to its conclusion, I would like to take a minute to thank everybody involved in making it a huge success. My special thanks to our HOD Professor Vishwanathan for his unwavering support at each and every step. Congratulations to the entire metal and materials team for pulling off the event so smoothly in so little time. Thank you to the students of the department for turning up in such huge numbers and making this event a huge success. Luckily, my parents are too present in the audience today and I cannot miss this opportunity to thank and acknowledge their constant support and motivation at every point of this